Alright, Module 7, Navy Electricity Training Series, Module 7, Chapter 3, Special Devices. Upon completion of this chapter, you will be able to explain the basic operation, major applications, Xenear diode, descriptive and basic operation, and tunnel diode or varactor. Explain the basic operation silicone rectifier through the TRIAC compared with the advantage and the disadvantage of each. List the 5 most commonly used optoelectric devices. Explain their use of each. Describe the basic operation, application, major advantages of the unijunction transistor. Describe the basic operation, application, major advantages of the field effect of the transistor with the metal oxide semiconductor field effect transistor. Explain the basic operation, major applications, Xenear diode. Describe the basic operation, tunnel diode, and vectors. Explain the basic operation, silicone control rectifier in the track. Compare the advantages and disadvantages of each. List 5 most commonly used optoelectronic devices. Explain the use of each. Describe the basic operation, application, major advantage of the unijunction transistor. Describe the basic operation, application, major advantage of the field effect of a transistor to this metal oxide semiconductor field effect of the transistor. Alright, introduction to special device. If you consider the sense of the nature of the various interacting properties of the semiconductor, the issue would not some surprise that the solid-state device that can be designed for many different purposes. In fact, with the device with a special feature for some of the numerous new designs so frequently introduced that it would be beyond the scope of the chapter to describe all of the devices in use today. Therefore, the chapter will include the various representative devices that are used extensively in the Navy, the equipment to give it an idea of the versatility that have been made possible. The devices have been grouped into 3 categories: diodes, optoelectrical devices, and transistors. In each chapter, each of the devices will be described in the basic operation. Each one will be discussed. Diode. The diodes are Diodes are 2-terminal semiconductor variables for the seeming endless for the application, for the operation, for the normal, the positive, and negative junction. Diodes have already discussed. There are a number of diode special properties of which should be familiar with the discussion of all of the development of the diode field within possible study. The more commonly special diodes have been selected for the explanation. These include Xenear diodes, tunnel diodes, reactors, silicone controlled rectifiers, and triacs. Xenear diode, the positive negative junction diode with the reverse bias to the matrix carrier, the holes on the positive material electron with the negative material moved away from the junction of the barrier. The depletion of the region becomes wider and illustrated figure 31. View A, view B, view C. The majority of the carrier current flows become very difficult across the high resistance with the wide depletion region of the major presence of the minority carriers caused with a small leak of the current that remains nearly constant with all the reverse voltage with certain values. One of the values have exceeded the sudden increase of the reverse voltage. The voltage will suddenly increase with the current occur with the breakdown of the voltage, or breakdown of the reverse current increase with the rapidity with a slight increase of the reverse voltage, and the diode can be in reverse bias to make the point of breakdown. But not every diode can easily dissipate with the power associated with the breakdown of the Xenear diode. The positive negative junction is designed to operate the reverse bias breakdown region. 3.1 show the effect of the bias depletion range for the positive negative junction. Depletion range positive negative barrel potential no bias. Reverse bias. These effects of the bias depletion region from the positive negative junction. Forward bias, the effect of the base of the depletion of the region and positive negative junction. The 2 distinct theories that explain the power of the negative junctions during the breakdown, with one of the Xenear effect, the other is the avalanche effect. The Xenear effect was first discovered by Dr. Carl Veneer in 1934, according to Dr. Xenear theory of the electrical breakdown with the solid electronics. Solid electrics occur with the process of the quantum mechanical tunneling. The Xenear effect for the account with the breakdown with below the 5 volts, where above the 5 volts the breakdown called for the avalanche effect. And although the avalanche effect is now accepted with the explanation for the diode breakdown, the term Xenear diode is used to cover both the type of the true Xenear effect of the semiconductor can be described in terms of the energy bands. However, only the 2 upper energy bands insert with the upper band with the illustrated figure 3.2 view A with the call with the conduction band and valency bond. Conduction band and valency band. Conduction band and forbidden gap valency band energy diagram of the Xenear diode. The conduction band is the band with the energy level of the electrons high enough that the electrons will move use under the influence of the external fluid. Feel the sense of the current flow with the movement of the electrons readily mobile. The electron conduction band are capable of maintaining the current through the external field with the form of the voltage supply. Therefore, the solid material have many of the electrons conduction band are called conductors. The valency band is the band where the energy level is the same as the valency electrons of the atom. Since the electrons in these atoms attached to the atom's electrons not freely to move around with the conduction band with the proper amount of energy added. However, the electrons of the valency band may be elevated with the conduction band energy level. To do this, electrons must cross the gap that exists between the valency band energy level and the conduction band energy level. The gap is known as the forbidden energy band or forbidden gap. The energy difference for the cross of the gap that determines whether the solid material will act as a semiconductor or insulator. A conductor material in which the forbidden gap is known as that can be considered non-existent with the semiconductor cell with the containment of the forbidden. The gap is shown in Figure 3.2 with the view A with the normally semiconductor with no electron with the conduction band. Energy level, the energy provided with the room temperature heat is enough of the energy to overcome the bending force with the free valency with the electron to elevate them to the conductor band energy level. The addition of the impurity of the semiconductor material incredible with the free of the electron with the conduction band and the number of electrons valency bands that can be elevated to the conduction band insulators of the material orbiting gap. The some large, practically no electrons can be given into the energy to cross the gap. Therefore, unless extreme large amounts of the heat energy are available, these materials will not conduct electricity. View B, Figure 3.2 with the energy diagram of the reverse bias of the Zener diode. The energy band of the positive and negative materials naturally in a different level, the reverse bias with the valency band with the positive material to overlap with the energy level of the conduction band with the negative material. Upon the condition with the valency of the positive material can cause the extremely junction region that overlap the point without any of the additional energy. The action is called for the tunneling of the breakdown point over the negative junction reach for the large number of the minority carriers tunnels across the junction from the current of the other curves break down. The tunnel phenomena only takes a heavily doped diode such as Zener diodes. Figure 3.2b shows the energy diagram of the Zener diode. Positive and negative current. Your energy conduction band, forbidden valency band. The second theory of the reverse breakdown effect of the diodes is known as the avalanche breakdown that occur with the reverse voltage beyond 5 volts. For the type of typical breakdown with the diode with the depletion region deliberately made known the narrow with the depletion region with the normal with the positive negative junction diode, but thicker than the Zener effect of the diode with the thicker the depletion region is achieved with the decreasing the doping level of the level of the Zener effect of the diodes. The breakdown with the higher voltage becomes because of the higher with the diversity of the material, the controlling the doping level of the material during the manufacturing process can produce breakdown voltage ranges between 200 and 200 volts. The maximum mechanical avalanche breakdown with the different with the Zener effect with the depletion of the region of the positive negative junction. Thermal energy is responsible for the formation of the electronic hole for the pair of the leakage of the currents caused by the movement of the minority electron with the electrically stated electrical field across the barrier region. After the reverse voltage drop with the depletion region and increase with the reverse voltage eventually reach with the critical view with the other critical breakdown voltage has been reached. Sufficient energy is gained with the thermal release minority electrons to be enabled to electrons rupture with the covalent bond as they collide with lattice. The release electrons are also accelerated with the electrical field resulting in release of the further electrons, so on, and chain the effect of the avalanche effect process illustrated in Figure 3.3. Figure 3.3 shows the avalanche of multiplication, the free electrons, positive, negative, for the reverse voltage slightly higher for the breakdown of the avalanche effect of the relief of the almost and the unlimited number of the carrier of the diodes essentially become the short circuit of the current flow for the region of the limited only by the external source theory for the current limiting resistor. Operating diode for the breakdown region that does not damage as long as the maximum power dissipation rating of the diode does not exceed the remove of the reverse voltage permits all carrier to return with the normal energy value and velocity. The symbols used within the Zener diode are illustrated in Figure 3.4 of the view B, view A, view B, view C, view D, view E. Note that the polar marking with the indicate the electron flow is in the area of the symbol that indicate against its normal positive negative junction diode. The breakdown diodes are operated in reverse bias mode, which means the current flow with the minority with the current carriers. Figure view 3.4a shows the schematic symbol of the Zener diode. Also, this shows the schematic symbol of the Zener diode and the schematic symbol of the Zener diode, also a schematic symbol of the Zener diode, also the symbol of the schematic diode, symbol of the Zener diode. Zener diode varies for the sort of the view of the many purposes, but the most widespread view of the voltage of the regulators only for the breakdown with the voltage of the Zener diode is read for the voltage across the diode must also contain with regardless of the supply of the voltage they are hold the voltage across the load at the constant level of the character of the Zener diode idea with the voltage regulator that can be found with almost all solid state circuits and capacity. Or the tunnel diode. The 1958 Leo SK, the Japanese scientists discovered the semiconductor junction diode with a heavily doped with impurities will have the region with the negative resistance for the normal junction diode, usually semiconductor material with a lightly doped the one impurity atom of the 10 million semiconductor atoms on the low doping level. The result of the relatively wide depletion region of the conduction occurred with the normal junction diode only if the voltage applied was large enough to overcome the potential barrier of the junction. The tunnel diode with the semiconductor material with the form of the junction is doped with the extent of the 1,000th of the impurity and with the 10 million semiconductor atom with having the doping procedure with extremely narrow depletion zone with a similar to the Zener diode as because of the heavily doping of the tunnel diode exists the unusual current voltage characteristic of the curve of the compared with that of an ordinary junction diode with the characteristic of the curve of the tunnel diode is shown in figure 3.5. Alright, your dotted dash line is standard positive negative junction. The full line is the tunnel diode at points 1 through points 5 and then indicate the progression of the curve. Voltage in millivolts and current in amps. Three most important aspects of the characteristic of the curve of the forward current increase of the peak or the small applied force of the bias, the degree of the forward current with the increasing of the forward with the bias of the many value of the current. Normally, 3, the normal increased forward current, further than increasing the bias voltage of the portion of the characteristic curve between the increase to the peak and the increase of the forward bias of the valley current is the region of the negative resistance explanation for the tunnel diode have the region of the negative resistance is better understood the evening energy levels and the previous explanation for the Zener effect. Simply state that their theory is known with the quantum mechanical tunneling of the electron possible positive negative junction without having sufficient energy to do so, otherwise by heavy doping width of the depletion of the region is 1 millionth of an inch. You may think of the process simply as an arc over the negative and positive side across the depletion range. Figure 3.6 shows the equilibrium energy level of the diagram of the tunnel diode with no bias supply. Note that view A with the valency band with the positive material overlap with the conjunction band with the negative material. The majority of the electrons hold with the same energy level of the equilibrium state. This is a movement of the current carrier of the depletion region with the thermal energy. The net current flowing through the zero becomes the equal number of the current carriers flow with the opposite direction. Zero net current flows in march over the zero current voltage curve illustrated in view B. Figure 3.6a shows the tunnel diode energy diagram with no bias. The energy level of the valency band between the conduction band and negative type of valency of the conduction. Now there's it's like staggered. 3.6b the tunnel diode energy diagram with no bias. The negative dash line with the same positive negative junction. And the line shows the tunnel diodes from points 1 through 5 to indicate the progression of the curve of the voltage in millivolts from 100 to 500 millivolts for the current amperes. Figure 3.7 of the view with A with a show of the energetic arm of the tunnel dyno with a small forward bias with the multi-volts of the lab with the bias current of the cow is the unequal level between the sum of the majority of the carriers that have the energy overlap at the point with not enough of the potential difference of the carriers across forbidden gap the normal manner with the sum of the same since the valence band with the positive material with the conduction band with the negative material still overlap the current carrier of the tunnel across the overlap the causing substantial current of the amount of the current that's marked with the point 2 on the curve of the view B with the note the view A with the overlap between the valency and the conduction band decrease the forward bias has been applied was applied. Figure 3.7 shows the tunnel diode energy diagram at 50 millivolts bias the energy level of the valency band with the conduction band with the forbidden band with the forbidden band with the valency band with the positive negative type. The show the view 7b for the tunnel diode anagram the 50 millivolt with the standard dash with the standard pin and positive negative junction. Also the full line of the tunnel diode with the points 1 through 5 indicate the progression of the curve. The voltage in millivolts, amp and currents and Figure 3a with a view of the energy diagram of the tunnel diode with the forward bias have then increased to 450 millivolts. As you can see, the valency band with the conduction band no longer overlap. At this point, the tunneling can no longer occur. The portion of the curve of the viewpoint, view B, with the point of the 2 and point 3 show the degree for the current across the bias, the increase of the area of overlap becomes smaller overlap between the two energy bandwidth becomes smaller and fewer electrons come the tunnel across the junction. The portion of the curve of the point 2 and 3 will the current decrease with the voltage increase with the negative resistance to the region of the tunnel diode. Figure 3H of the tunnel diode energy diagram of the 550 millivolts of the positive, the negative, and the conduction band and the valency band conduction forbidden gaps. View 3-8B shows the tunnel diagram, diode energy diagram at 450 millivolts. Standard pipe positive negative junction tunnel diodes 0.1 through 5 indicate the progression of the curve. And figure 3-9 show the view A of the energy diagram of the tunnel diode with the forward bias tab. Then increase even further the energy bands no longer overlap. The diode operates with the same manner for the positive negative junction. Normal positive negative junction is shown with the portion over the curve of the view B with the 0.3 and 4 over the show the 3-9A of the tunnel diode energy diagram of 600 millivolts. The conduction band forbidden gap and balancing the power of the have been matched. B. The tunnel diode energy diagram at 600 millivolts bias for the standard negative junction. The tunnel diode at points 1. The negative of the resistance the region of the most important, most widely characteristic for the tunnel diode based on the operative of the negative resistance reading can be either an oscillator with the amplifier with a wide range or frequency application, very high frequency application, the tunnel diode with the possible to become with the tunnel action occur so rapidly that there's no transit time and effect, but therefore no signal distortion. The tunnel diodes are also extensively high speed with the switching circuit because of the speed of the tunneling action. Several schematics are used to indicate the tunnel diode. These symbols are illustrated in figure 310 with the view A, view B, view C, view D. Show the 310 show the tunnel diode schematic, the tunnel diode with the schematic, the 310B, 310C show the tunnel diode schematic, tunnel diode schematic symbol, your varactor. Your varactor and varicap, the schematic diagram of the figure 11, the diode with the behavior of the variable capacitor with the positive negative junction function with the dielectrical place of the common capacitor and various factor operates with an important prerequisite to understanding the field effect of the transistor, which covered in later in this topic. Figure 312, figure 11 throws to the varactor diode. Figure 312 is the positive negative junction surrounding the junction of the positive negative material. And now the region voided post both positive and negatively charged with the current carrier of the air is complete called the depletion region. The depletion region over the positive and negative junction. The side of the depletion region with the vector of the diode is directly related to the blast forward biasing made for the region with the small with the repelling with the current carrier of the with the positive and negative junction applied with the voltage of the large enough with about a half a volt of silicone material. Now the particle will cross the junction and join with the positive particle with the shown figure 313. The forward biasing called the depletion region that decreases, perceiving low resistance of the positive and negative junction, large current with the flow of the cross. Thus the condition of the forward bias diode. On the other hand, reverse bias with the voltage applied with the positive and negative junction side of the depletion region increase the charged particles on both sides of the move away from the junction. The condition shown with the figure 314 produced with a high resistance between the terminals, alloys with a low current flow with only the microampere range. The operating condition from the vector diode with is nothing more than a special positive negative junction. 313 show with the forward bias positive negative junction. Also the 314 show with the reverse bias positive negative junction. The gap has been increased. As a figure, you show the insulating figure, insulating gap formed with the reversing by with the vector, with this complete with the layer with the electrical materials between the plate of the common capacitor. Further formula is to calculate the capacity. Capacitation is equal to plate area times the constant value over the distance between the plate. Can it be applied with both vector with the capacity and the same case for the side of the insulation gap with the vector of the depletion region? Substitute with the distance between the plate with the capacitor by the varying with the reverse by with the applied with the vector with the width of the gap that may be varied. Increase with the reverse of the bias width of the gap reduce the capacitation C with the positive negative junction. Therefore, the capacitance C with the vector is increased with the potential with the applied with the reverse bias. The ratio of the vector capacitance C with the reverse bias voltage change may be as high as 10 to 1 with the figure with the 315 show with the one example of the voltage capacitance C ratio of the VUA show with the reverse bias at 3 volts producing capacitation of 20 microfarads picofarads of the vector. The reverse bias increase with 6 volts as shown the UB the depletion region widens the cover the drop to 5 picofarads and each with each 1 volt increase with the bias voltage with the cover of 5 picofarads increase with the capacity of the vector of the ratio of the chain with therefore 5 to 1 over the course of the decrease of the applied bias voltage would cover the proportionality of the increase of the capacity of the depletion region narrows. Notice the value of the capacitance is small in the picofarad range. 315, the vector capacity versus bias voltage. Depletion range, 20 picofarads, 5 picofarads. In general, the vector, you believe the old style variable capacitor tuning, they use the tuning circuit with sophisticated communication equipment and other circuits with the variable capacitation. The core of the own advantage of the vector is all with the DC voltage to be used as a tune circuit as a simple remote control or the auto tuning function with one of the such application vectors, the variable time tuning capacity received with the transmitter tank circuit with the like shown with figure 316. Figure 316 show the vector turn reside side. You have your induction coil, your capacitor, your capacitor 1 and 2, your vector, RFC and resistor. Alright, figure 316 show the DC voltage of the belt of the wiper with the penometer with the resistor 1, which can be adjusted between voltage positive and the voltage negative. The DC voltage path with the low resistance of the radio frequency of the choke with the L2 with the axis of the reverse bias with the vector diode capacitor C3 the capacitation C3 and series with the capacitor C2 equivalent capacity with C2 and 3 in parallel to the tank of the resistance and capacitation of the induction of the capacity, and therefore the variation of the DC voltage resistance variable for the capacitation capacity of the C3 capacitor C3 the resultant frequency of the tank circuit, the radio frequency choke for the provide for the inductive read for the tank frequency to prevent the tank loading with the resistor 1 and capacitor 2, extra allow the DC from as well as the fixing the tuning range of the capacitor to the C3 ohmmeter can be used with a check of the vector diode with a circuit with a high reverse resistance and low forward bias resistance. The 10-to-1 ratio of the reverse bias with the forward bias resistance is considered to be the normal. Silicon controlled rectifier, or SCR. Silicon controlled rectifier, usually referred to as the SCR, with the one family of semiconductor include the transistor and diodes. Drawing of the silicon controlled rectifier is the schematic of the representation shown in view A and B of figure 3017. Note, not all silicon controlled rectifiers use the casing shown, but this is typical most in high power units. Show the A, show the high power unit with the gate lead, the cathode lead with the anode. Your silicon controlled rectifier with the schematic drawing the anode gate lead and the cathode lead. Although this is not the same with either the diode or the transistor, the silicon controlled rectifier combined with the feeder feature of the both of the circuit of the transistor, the rectifier may be greatly improved with the use of the use of silicon controlled rectifier. The basic purpose of the silicon controlled rectifier function is to switch the turn off the on of the small large amount of the power. If the form of the function no moving parts of the wear out with no points required for the replace with the tremendous power of the silicon controlled rectifier with the summing unit of the small triggering current is able to switch several thousands of the amperes without exceeding the rated ability with the silicon controlled rectifier often to replace the slower large mechanical switch have many advantages over the more complex large electron tube the equivalent thiatron. The silicon controlled rectifier is extremely fast switch. The difficulty to cycle the mechanical switch several hundred times a minute, but yet the silicon controlled rectifier can switch to 25,000 times a second. It takes just a microsecond, a millionth of a second to turn off these joints. Whether the very type of the switch can be carried with the type of the regulator for the amount of the power flowing from the switch for the sum of the devices operate pulse of the power of the alternating current in the special form of the alternating positive negative pulse. Silicon control rectifier can be used readily with the control application. Most speed controllers, the inverter of the remote switching unit, the control rectifier circuit overload, protective latching relays, computer logic circuits are all used with the silicon control rectifier. Silicon control rectifier made over the four layers of semiconductor material with the positive, negative. The construction is shown with the UA with the figure 3.8 over the function of the silicon control rectifier has much of the common with the diode, but their theory of the operation of silicon control rectifier is best explained in the term of transistors. Figure 318 shows the silicon control rectifier structure. The anode jump 1, jump 2, jump 3, positive, negative jump of the cathode from the anode on the gate. Consider the silicon controlled rectifier transistor pairs of one positive, negative, and other negative, which is connected to shown with UB with the UC anode is attached to the upper P layer of the cathode C. It's now part of the N layer, negative layer of the gate terminal go through the positive layer of the negative triode. Figure 318 shows the silicon control rectifier with the two transistor equivalent. The two transistor schematic for the silicon control rectifier, the transistor 1 and transistor 2, A and B, beta 1, beta 2. The operation of the collector of the transistor, the device of the base of the transistor 1, with the collector transistor 1 feeds back with the base of the transistor 2. Beta in general term of the current transistor 1 and beta 2 with the current gain of the transistor 2. Give the positive feedback with a loop of the product with 1 times 2. The product less than the 1 of the circuit is stable. The product with the greater than unity of the circuit with the regeneration small negative current applied with the terminal G will be gaze. By of the negative positive transistor cut off the loop again is left with the unity under these conditions. The only current that can exist with the output of the terminal A and C with a very small cutoff electric current of the two transistors for the reason the impedance between A and C is very high. Alright, when the positive of the current is applied with the terminal G with the transistor Q2 with the Jthon in the conjunction with the cause of the collector to cutting current to arrive at the sense of the current gain with the transistor 2 with the increase the collector current with the point of the call with the break over the point reached with the loop with the gain equal for the unity circle to become with the regenerative of the plow of the point of the collector current with the two transistors rapidly increase the value with limited only the external circuit of both the transistors driven in with the saturation impedance of the value A and T. Very low positive of the current is applied with the G, but the serve with the trigger with the self-generation act with no longer the required with the sense of the collector with the positive negative transistor 1. Now the supply with more than enough of the current to drive the current transistor 2. The circuit will remain until it is turned off with the reduction of the current collector current to the value with the below with the necessary to maintain conduction. The character of the curve of the silicone-controlled rectifier shown in Figure 319, no gate current leakage of the current remains very small with the forward from the cathode anode until the breakdown point with the reach of the center junction of the breakdown silicone-controlled rectifier begins with the conductive heavy and the drop of the curve of the silicone-controlled rectifier becomes very low. Figure 319 shows the characteristic curve of the silicone-controlled rectifier for reverse voltage leakage voltage with the reverse current, forward current, high conducting holding current, forward leakage current with the breakage voltage, forward voltage. The effect of the gate signal firing when the silicone-controlled rectifier shown in Figure 320 breakdown with the center of the junction achieved with the speed of the approaching microsecond applying with the appropriate signal of the gate lead with the holding the anode voltage constant with the after breaking down the voltage across the devices so that the current with the through it for the cathode anode is essentially terminal loading is feeding. Maximum reverse voltage, reverse blocking region, holding current with a high condition region, the floor blocking region, forward breakover voltage. The important thing to remember: the small current for the gate and the cathode can fire with the trigger with the silicone controlled rectifier chain with practically an open circuit with a short circuit with the only way to think chain the back again with to communicate the reduce the load current with the value left of the minimum forward bias current. Gate current is required with only with the ordinary current with the completing between the point sufficient to sustain the connection between about 5 microseconds with the resistant level loading circuits. After the conjunction from the cathode anode begins reaching with the gate current has no effect. Basic operation silicone controlled rectifier compared with that with the titron with the electron electron tube with normally gas filled with the filament with the heater the silicone controlled rectifier and the titron function in very similar manner. Figure 321 show the schematic of each of the corresponding elements labeled in both the type of the device controlling with the input signal is loft as they after the trigger with the control grid titron and the gate with the silicone controlled rectifier with no further input with the magnitude low current after the conduction begin with the low current can be interrupted by one or more of three methods. Load circuit can be must open by the switch of the plate with the anode voltage must be reduced below the ionizing potential for the gas titron with the 3. The forward biasing current must be reduced below a minimum value with the required to sustain the condition with the silicone control rectifier. The input with the resistance of the silicone control rectifier level to the low. Approximately 100 ohms requires the current with the triggering input resistance of the titron especially high with the required voltage input with the grid of the triggering action. Figure 321 shows the comparison with the silicone control rectifier and titron, the cathode, the anode, the grid, the gate, the plate. Silicone control rectifier on the left, and then the titron on the is B. The application of the silicone control rectifier, and even the fact that many application rectifier would give the semiconductor device the name of the alternating current supplied with the rectifier only with the power with the negative half of the sine wave through. Each of the positive and negative half cycle will appear for the output of the silicone control rectifier. However, the control rectifier may be turned at any time during the half cycle with the controlling amount of the DC power available to 0 to the maximum shown in Figure 322. Since the output is actually DC pulse suitable filtering can be added with the continuous direction, but any of the DC operated devices can be controlled amount with the power to apply, but they know that the silicone control rectifier must be turned in the desired time each of the cycle. Alright, show the zero firing with 180 conduction angle, the gate pulse with the phase for the zero max output with the gate and 90 degree firing angle, the condition angle, the phase delta y, delay y with 90 half of the output wax. Max 180 firing degree condition angle with the gate pulse with the phase delay of 180 output with the output. Alright, when arc powers you with the silicone control rectifier turn automatically since the current of the voltage drop to 0 to every half of the cycle with the evening silicone control rectifier positive alteration of one negative whole wave of the rectification can be accomplished with controllers of the time over the entire sine wave of the silicone control rectifier shift the application just as the name supplied with the silicone control rectifier of the AC voltage to the triac. And we're going to cut the tape there.